All right, so now we're moving on to kind of the second most important thing, okay, in this unit, and that's acceleration. So we've talked about things moving at a constant velocity. We've done our vector addition stuff. Okay, now we need to look at situations where the velocity of the object changes. Okay, now remember, in physics, there's only acceleration. We don't typically use the word decelerate. Okay, there's acceleration that's positive or negative, and acceleration is any change in velocity. That's point number one. Okay, what is accelerated motion? Accelerated motion occurs when there is a change in velocity over time. Right? Okay. Relationship between change in velocity, distance, time, and acceleration. Basically, we're going to be looking at a whole bunch of new acceleration formulas. Right? Last year, the only acceleration formula that you had was this one. Okay? It may have been written like this, delta V over delta T, depending on who you had. Okay? But yeah, change delta, change it. Yeah. Okay. That's the way you would have had it. That was the only one you would have used in Science 10. Okay. We're going to go over 4 more. All right. It gives you a much greater ability to calculate things when you have a wider variety of formulas.
Is that the one with the triangle?
No, it is not the one with the triangle. You can't use triangles. If you're still using triangles to manipulate equations, you should drop my class. Because yeah, it's just not going to work. It's just not going to. Okay? Yeah. I don't mean that to be cruel. I'm just being perfectly honest with you. Okay? If you don't know what I mean, because Easton just wants me to go on a rant again here. Okay? But in case you don't know what I mean, somewhere along the way, some well-meaning but wrong person taught you that you can manipulate equations by doing this. And if you cover up what you're looking for, it gives you the formula. And, okay, while that works for this formula and any other 3-variable formula, it, A, doesn't teach you how to do algebra, which is kind of important. Okay? And it won't work for this one. T equals 2 pi times the square root of L over G, which you'll be using in Unit 3. Nice. Okay? Or this one that you'll be using in Unit 4, F1 equals F0 times the, sorry, I'll put this in brackets, times in brackets speed of the source plus or minus the speed of the waves over, sorry, of the observer, speed of the source plus or minus the speed of the waves. Okay, that one I'm pretty sure there's no triangle for. Yeah, stuff like that. Okay, yeah. See, the triangle's a crutch, and I'm the guy who comes around and kicks your crutch out. Okay, I'm the guy who helps you learn to walk without a crutch. Okay, so I'm the good guy here. Okay, just so you know, even though I'm the guy who kicks the crutch out, I'm the guy who teaches you how to walk. Right? So yeah, you can't use triangles. If you do, and you don't know how to manipulate equations for algebra, today is going to be very difficult. Okay. All right. So, whenever the velocity of an object is changing, we say the object is accelerating. Okay? The meaning of average acceleration is best illustrated by a plane taking off. Okay? And that is because the acceleration is uniform. Right? It changes, the velocity changes evenly over the course of the entire movement. Okay? So if I was looking at a plane during takeoff and I was looking at its velocity versus time graph, it would look like this. It would be very linear, right? Because a plane doesn't have gears, right? It just push the throttle forward and it just goes faster. Okay? A car accelerating away from a stoplight is a terrible example of uniform motion because a car has gears. In first gear, you accelerate pretty substantially, but as you change gears, the acceleration flattens out, and eventually you can't accelerate anymore, right? So it's a bad example of uniform acceleration. Right? Everybody follow the difference there? Okay, so we're going to be dealing with uniform acceleration in all of the problems that we solve. Okay, so acceleration is the change in velocity divided by the change in time. That's where this formula comes from. this formula also comes from the graph I just stupidly erased. Okay, so I got meters per second, I got seconds, okay, this is time. So if I've got a nice linear relationship here, okay, this is showing an object whose velocity is no. But this is velocity on this axis. What's happening to the velocity? Yeah, it's accelerating. It's increasing, right? This graph is showing the velocity of the cart, and the line's going up. Everyone follow there? And so this object is increasing its velocity. It is accelerating. All right. If I was looking at this graph, it would say y equals m times x plus b. Right? The slope of this graph would be y minus b over x. That would be, y minus b would be the change in velocity. And x would be the time. That formula you used is calculating the slope of a line on a velocity versus time graph. In the same way that slope calculated velocity from a position versus time graph, because they're both the change in y divided by the change in x. In this case, y is velocity. Okay, everybody with me there? All right, so that's where that formula comes from. All right, so if we're looking at a very simple acceleration problem using last year's acceleration formula, we might have something like this. Okay, so we have this plane that at time 0 is at rest. What is rest? It stops, right? If anything is at rest, okay, or starts from rest, its initial velocity is 0. If it comes to rest, right, it goes to 0. Its final velocity would be 0. Just things to watch for when you're reading a question. Okay, so it's at rest at time 0. Okay, the plane accelerates down the runway for 29 seconds and reaches a velocity of 72.2 meters per second. Okay, we want to determine the average acceleration of the plane. All right, so what we have is this. Okay, we know the time is 29 seconds. We know the initial velocity is 0. The final velocity is 72.2 meters per second. Okay, and we're looking for the acceleration. All right, so if I have those things, I can use this formula, Vf minus Vi over t. This, guys, is why we give you a mark for writing down your givens. You are going to have 5 different acceleration formulas. Writing down your givens helps you determine which one you are going to use. Okay, it's kind of like you got to match it up. You got to find, okay, this formula has A, which I'm looking for. It has Vf, which I have, Vi, which I have, T, which I have. I can use that formula. Okay, I know everything but one part of it, and that's the way you'll do this. So that's why you get a mark.
Are you going to have to memorize it?
You will not, because you will always have your formula sheet. Okay? Yeah. All right, so if I'm calculating the acceleration here, then I'm just plugging in the numbers. 72.2 minus 0 divided by 29, okay, and that would give me the acceleration of the plane, 2.5 meters per second squared. Now, don't get confused here. The squared doesn't mean the number squared. Sometimes people do that, okay? It means the units are squared. Okay, and the units are squared for this reason. When I divided meters per second by seconds, okay, I got meters per second. Okay, that's the rate of change of velocity. I'm changing my velocity by this many meters per second, right? Well, if we actually do that like it's fractions, okay, divided by seconds, okay, I'm basically saying this, right? Right? Meters per second divided by seconds, which is the same as seconds over 1. If I'm dividing fractions, what do I do with the second one? Yeah. Okay, I flip and, yeah, or multiply. Okay? I don't know who taught you that, but that's fine. Okay? So, I reciprocate and multiply. That's how I say it, because it doesn't sound creepy. Okay, so meters times 1 is meters, seconds times seconds, seconds squared. Okay, that's where we get those units from. Meters per second per second. All right, everybody okay with that? Okay. So that formula you guys should be pretty familiar with because you've used it before. All right, here are our other formulas, the other 4 acceleration formulas. And they don't actually all have acceleration as the thing they're solving for. It's just part of the equation. Right? Our first one here has to do with, again, a velocity versus time graph. Okay, so here's our meters per second, here's our seconds, okay? And we have a nice linear relationship on here. Right? This is solving for displacement. How on a velocity versus time graph do I find displacement?
Velocity initial times time plus 1.
No, how from the graph? What do I do from the graph? The area under the line. Okay, does everybody remember that from before? Okay, we said that was like taking average velocity times time. Well, that's what we're doing. Okay, this formula right here, okay, this one here, calculates the area under the line. VI times t, this is our initial velocity right here. Okay, it's how fast we were going at time 0. And we're multiplying it by the time. That's the base times the height. So this part here is VI times t. Right? This part here is taking 1/2 times the acceleration times time. That's essentially finding the area of this triangle. Okay? It's like 1/2 base times height. I know it doesn't look that way, but that's what it's doing. Okay? It's taking the rate of acceleration, halving it, and multiplying by the time squared, which is the same as taking meters per second times seconds.
Is this just for uniform velocity?
Yes. Now, these formulas will, I mean, basically everything we do is uniform. You could do this, but you'd be extrapolating a little bit. You know. Okay? Everybody with me there? All right. The next formula looks a lot like the first one, except it relates from the final velocity. It goes VF times t minus the 1/2 at squared. So what it's doing is, okay, it's going, here's VF. It's multiplying by time, so it's calculating this whole big rectangle, and then it's subtracting this. It's still calculating the area under the line. Okay? It's just doing it from a different angle. Right? Everybody okay with that? So that's where we get those 2 formulas from. You will use these formulas a lot. Okay? Of course, you'll use them a lot. Okay, the third one here, VF squared equals VI squared plus 2AD. Okay, that one will come into play quite a bit when we're in projectile motion, which is the end of the unit. Okay, we're talking about it and using it a lot then, right? But it's just essentially it'll calculate any part of this as long as it's manipulated, right? And then this last one here, okay, D equals VF plus VI divided by 2 times T. Really, all this is this. Okay, it's really average velocity equals displacement over time. This only works, though, for uniform acceleration. Okay, the other ones will work for non-uniform. They're extrapolating, but they'll work. This one won't. Okay, the acceleration has to be uniform for that, except for that formula. All right, questions on that? Don't pack up. That's it. I can see what time it is. Okay, I want you guys to try that question right there. That's using last year's acceleration formula. See if you can solve it. We'll go through it before the class ends. Okay, solving this one. First thing, write down your givens. Hybrid car, initial velocity 10 meters per second east. Okay, it accelerates at 3 meters per second squared east. Okay, how long will it take? We're looking for t to acquire a final velocity, vf, of 25 meters per second east. All right, so those are our numbers. Okay, we'll be using this formula and manipulating it for t. So I'll multiply both sides by t, divide both sides by a. Okay, and I'll have that. Okay, so we'll have 25 minus 10 divided by 3. Okay, so 15 over 3, 5.0 seconds. Well, I don't know what that's seconds. Okay, we'll go over some more of those tomorrow. Lots of acceleration stuff tomorrow.